In the frozen darkness beyond Neptune, 5 human-made objects are writing the first chapter of interstellar exploration. Voyager 1 has traveled over 15 billion miles from home, farther than any object humanity has ever built. Now, they are drifting through alien space between the stars. These cosmic scouts have shattered every prediction, discovering volcanic moons that shouldn't exist, violent storms larger than planets, and mysterious regions of space that rewrite our physics textbooks. They carry golden messages for alien civilizations and photograph our entire solar system as a pale blue dot. If you're ready for this journey, hit that like button and join Stellify Science as we explore the edge of everything we know. Prepare yourselves. We begin. On August 25th, 2010, a washing machine-sized spacecraft broke through an invisible barrier that no human creation had ever crossed before. Voyager 1 had been traveling for 35 years when it finally breached the heliosphere. This is the massive bubble of solar wind surrounding our entire solar system, like a cosmic soap bubble, protecting everything we know. This wasn't just any boundary crossing. The probe had officially entered interstellar space, becoming humanity's first ambassador to the galaxy itself. Think of our solar system as a lighthouse beam, cutting through fog. The sun constantly blasts charged particles in all directions, creating this protective bubble that extends far beyond Pluto. For decades, scientists wondered what lay beyond this cosmic shoreline. Would Voyager 1 simply drift into an empty void? Would alien particles bombard it? Would its instruments survive the transition? The answer came through a stroke of luck and brilliant engineering. When solar storms erupted back on the sun, they sent shock waves pulsing through space like sound waves through water. These waves reached Voyager 1 and caused nearby electrons to vibrate, creating a cosmic tuning fork that revealed the density of space around the probe. The data showed something incredible. Voyager 1 had crossed into a region where the sun's influence finally ended. But here is what made scientists' jaws drop. The spacecraft didn't just cross a simple line in space. It discovered that the boundary between our solar system and interstellar space resembles a turbulent river meeting the ocean. Solar wind particles crashed against interstellar matter, creating complex magnetic fields and pressure waves that stretched for millions of miles. Voyager 1's instruments detected the change immediately. Solar particles dropped by 1,000 times, while galactic cosmic rays, ancient radiation from exploding stars, increased by 9%. The probe had entered a realm where radiation from distant supernova, created when massive stars died millions of years ago, now bathed its sensors. The spacecraft weighs just over 1,700 pounds and carries less computing power than a modern smartphone. Yet, this tiny machine had achieved something unprecedented in human history. It became our species' first presence in the space between stars, carrying a golden record with sounds and images from Earth for any alien civilization that might find it. Today, Voyager 1 continues racing away from the sun at 38,000 miles per hour. Every second, it moves another 11 miles deeper into territory no human has ever explored. Its radio signals take over 22 hours to reach Earth, and that delay grows longer with each passing day. The probe's nuclear power source slowly decays, giving it perhaps another decade of life. But its journey into the unknown has only just begun. What it discovers next will challenge everything we thought we knew about the space between stars. Voyager 1's instruments immediately detected something that made no sense according to every computer model scientists had built. The space between stars should be nearly empty. A cosmic desert with maybe one particle floating in every sugar cube-sized volume. Our sun creates a bubble of hot, thin plasma that pushes against this interstellar emptiness. Logic dictated that once Voyager crossed the boundary, it would encounter even thinner, colder material stretching between distant suns. Instead, the probe found space that was actually denser than the region it had just left behind. Imagine walking from a crowded room into what should be an empty hallway, only to discover the hallway packed with even more people. That is essentially what Voyager 1 experienced when it crossed from our solar system into interstellar space. The electron density jumped dramatically, defying every prediction physicists had made. This discovery forced scientists to completely rethink how our solar system interacts with the galaxy around it. The sun's solar wind, that constant stream of charged particles blasting outward, creates a shockwave as it plows through interstellar matter. Like a speedboat creating a wake, our entire solar system carves a path through the galaxy's thin soup of gas and dust. But here is where it gets really weird. The boundary region, called the heliopause, acts less like a smooth shoreline and more like a chaotic surf zone. Solar wind crashes into interstellar plasma, compressing it and heating it to temperatures reaching tens of thousands of degrees. This creates a turbulent mixing zone where particles from our sun collide with ancient matter that has drifted between stars for millions of years. Voyager 1's plasma wave instrument detected this density increase by listening to the vibrations of electrons around the spacecraft. When solar storms sent shockwaves racing outward from the sun, they caused these electrons to ring like bells. The frequency of this cosmic music revealed the true nature of interstellar space. The implications staggered the scientific community. If the space between stars is denser than expected, it means our galaxy contains far more matter than anyone realized. This hidden material could influence how stars form, how planets develop, and how entire solar systems evolve over cosmic time. The discovery also revealed that our sun's protective bubble is under constant pressure from forces beyond our solar system. Interstellar winds, created by shock waves from ancient supernovae, push against the heliosphere and shape its boundaries. We live inside a cosmic battle zone, where our star fights to maintain its territory against the galaxy itself. Even more remarkable, Voyager 1 found that this dense interstellar plasma carries magnetic fields twisted into complex structures by forces operating on scales larger than entire star systems. These magnetic highways could channel cosmic rays and other high-energy particles across vast distances, creating an invisible network connecting distant regions of the galaxy. But this plasma discovery was just the beginning of revelations that would transform our understanding of what lies beyond the familiar worlds of our solar system. When Voyager 1's cameras first glimpsed Jupiter's moon, Io, in March 1979, mission controllers thought their instruments had failed. The images showed a world that shouldn't exist. A moon covered in vivid yellows, oranges, and reds, with massive plumes erupting hundreds of miles into space. Scientists expected to see another cold, cratered rock like Earth's moon. Instead, they discovered the most volcanically active world in the entire solar system. With eruptions so violent they could be seen from 6 million miles away, Io experiences volcanic fury that makes Earth's most explosive eruptions look like minor tremors. The moon boasts over 400 active volcanoes, some shooting sulfur and molten rock 300 miles high. These eruptions are so tall, they would reach from New York City to Boston if they occurred on Earth. The sulfur compounds create a rainbow of colors across Io's surface, painting alien landscapes in shades never seen on any other world. But what makes Io's volcanoes possible defied everything scientists knew about planetary science. Moons should be cold, dead worlds. They lack the internal heat sources that drive volcanism on planets. Yet here was a moon smaller than Earth's, orbiting 5 times farther from the sun than Earth does, somehow generating enough heat to power volcanic eruptions more intense than anything on our home planet. The answer lay in a cosmic torture chamber called tidal heating. Jupiter's immense gravity, 318 times stronger than Earth's, constantly squeezes and stretches Io as the moon follows its elliptical orbit. This is like bending a paperclip back and forth until it becomes too hot to touch. This gravitational kneading melts Io's interior into a churning ocean of liquid rock. Making this torture even worse, Io gets trapped in a gravitational tug-of-war with Jupiter's other large moons, Europa and Ganymede. Every time Io completes one orbit around Jupiter, Europa completes exactly half an orbit, while Ganymede completes 1/4. This perfect mathematical relationship, called orbital resonance, prevents Io from settling into a circular orbit where it could cool down and find peace. Voyager 1's infrared instruments detected surface temperatures reaching 2,000 degrees Fahrenheit at volcanic hotspots, hot enough to melt copper. The volcanic activity pumps out 2 tons of material every second, constantly resurfacing the moon and erasing any impact craters. Io's volcanoes have completely renewed its surface dozens of times throughout the moon's history. The sulfur ejected from these volcanic geysers doesn't just fall back to the surface as it would on Earth. Io's weak gravity allows volcanic material to escape into space, where it forms a vast, donut-shaped ring around Jupiter. This ring, invisible to Earth-based telescopes, glows with the light of electrically charged sulfur particles. Even more bizarre, Io's volcanoes create their own weather systems. Sulfur dioxide gas from eruptions condenses into frost during the moon's brief night, then sublimes back into the atmosphere when sunrise returns, creating daily snowfalls of sulfur compounds. But Io's hellish landscape was just the first shock in a series of discoveries that would reveal how Jupiter ruled an empire of worlds, unlike anything in our solar neighborhood. Voyager 1's cameras captured something that had stayed hidden from astronomers for over 3 centuries of studying Jupiter: a thin, ghostly ring circling the giant planet. The discovery came as a complete surprise on March 5, 1979, when mission planners decided to take a long exposure photograph of Jupiter's dark side. They hoped to spot lightning in the planet's atmosphere, but instead found themselves staring at a delicate ribbon of light wrapped around Jupiter like a cosmic wedding band. Earth-based telescopes had missed this ring system entirely because it was simply too faint and too close to Jupiter's brilliant disk to be seen from our distant world. This ring system operates on principles completely different from Saturn's famous ice rings. While Saturn's rings shine brightly because they contain millions of chunks of reflective water ice, Jupiter's rings are made of microscopic dust particles, darker than coal. These tiny grains absorb most of the sunlight that hits them, making the rings nearly invisible, unless viewed from just the right angle with the sun behind them. The dust comes from Jupiter's innermost moons, Metis, Adrastea, Amalthea, and Thebe, which get constantly sandblasted by micrometeorites traveling at tens of thousands of miles per hour. Each impact knocks dust particles off these small moons, and these particles spiral inward toward Jupiter under the influence of electromagnetic forces. Think of it like cosmic erosion, where Jupiter's radiation and magnetic field slowly grind its moons into powder. But here is what made scientists realized they were looking at something extraordinary. The ring particles don't just orbit randomly around Jupiter. They are organized into distinct structures: a main ring, a gossamer ring, and a faint halo, each controlled by different physical forces. The main ring, only about 4,000 miles wide, contains most of the material and appears as bright as Jupiter's faintest moons when viewed from the perfect angle. Voyager 1's discovery revealed that ring systems aren't rare cosmic jewelry worn only by Saturn. Instead, they represent a fundamental process occurring throughout the solar system, wherever large planets capture small moons. The spacecraft found that Jupiter's rings extend from just above the planet's atmosphere to nearly 50,000 miles outward, a vast invisible disk of dust particles dancing in complex gravitational and electromagnetic fields. The rings also interact with Jupiter's powerful magnetosphere in ways that create their own aurora displays. Charged particles from Jupiter's radiation belts strike ring particles, causing them to glow with faint light visible only to sensitive instruments. This creates a dynamic light show happening continuously around Jupiter, invisible to human eyes but detectable by spacecraft cameras designed to peer into darkness. Even more fascinating, Jupiter's rings change constantly as new dust gets blasted off the inner moons, while older particles spiral into Jupiter's atmosphere and burn up. The entire ring system renews itself every few thousand years, making it a relatively young and dynamic structure compared to the ancient, stable rings around Saturn. The discovery of Jupiter's rings proved that our solar system contained hidden structures that had escaped detection for centuries. But this was merely the first glimpse of violent phenomena occurring in Jupiter's domain that would challenge every assumption about planetary weather systems. Voyager 1 detected radio signals from Jupiter that solved a mystery and revealed weather more violent than anything on Earth. The spacecraft's radio antenna picked up strange whistling sounds coming from Jupiter's night side. This was the characteristic signature of lightning discharges powerful enough to be heard across millions of miles of space. But these weren't ordinary lightning bolts. They were electrical storms, spanning areas larger than entire continents, with individual lightning strikes releasing more energy than all of Earth's power plants combined. Scientists had never observed lightning beyond Earth before Voyager 1's encounter with Jupiter. The discovery came when the probe's instruments detected rapid radio pulses, characteristic of electrical discharges. Following these signals like cosmic radar, Voyager 1 turned its cameras toward Jupiter's dark hemisphere and captured the first photographs of alien lightning. Brilliant flashes illuminating cloud tops from below like a photographer's strobe. These Jovian thunderstorms operate on a scale that dwarfs terrestrial weather. Individual storm systems can persist for months or even years, growing to sizes that would swallow multiple Earth-sized planets. The Great Red Spot, Jupiter's most famous storm, has been raging for at least 300 years and contains winds reaching 400 miles per hour at its edges, twice as fast as the strongest hurricanes ever recorded on Earth. But what makes Jupiter's lightning particularly amazing is where it occurs. On Earth, lightning forms in water clouds, where ice crystals collide and build up electrical charges. Jupiter's atmosphere contains no water at the altitudes where these lightning storms rage. Instead, the electrical activity happens in clouds made of ammonia ice crystals, floating in an atmosphere composed mostly of hydrogen and helium. The temperature difference drives this alien weather system. Jupiter's core burns at 24,000 degrees Fahrenheit, hotter than the surface of the sun, while the cloud tops freeze at negative 200 degrees Fahrenheit. This creates enormous convection currents that carry heat from the interior to space, generating updrafts and downdrafts that make Earth's most violent tornadoes look gentle. Voyager 1's instruments revealed that Jupiter actually produces more heat than it receives from the Sun. The planet generates twice as much energy internally as solar heating provides, making it almost like a failed star that never quite ignited. This internal heat source drives weather patterns that have persisted for centuries without any seasonal changes. The lightning strikes themselves release radio waves that Jupiter's powerful magnetic field amplifies and broadcasts across the solar system. These radio signals travel at the speed of light, reaching Earth about 45 minutes after the lightning flash occurs. Amateur radio operators on Earth had been detecting these mysterious signals for decades without realizing they were listening to alien thunderstorms. Even more remarkable, Voyager 1 discovered that Jupiter's polar regions, areas that receive almost no sunlight, host some of the most intense lightning activity. Unlike Earth, where lightning occurs mainly in tropical regions heated by the sun, Jupiter's lightning storms are powered entirely by the planet's internal heat engine. The scale of these electrical displays boggled the minds of atmospheric scientists. A single lightning bolt on Jupiter can stretch for thousands of miles and release enough energy to power New York City for several minutes. But these were just the first hints of the dynamic worlds hidden beneath the thick atmospheres of giant planets. Beneath the frozen surfaces of two seemingly dead moons, Voyager's cameras revealed the first clues to vast oceans that could harbor alien life. Europa, Jupiter's fourth largest moon, appeared in Voyager 1's images as a billiard ball smooth world, covered in a web of dark cracks, crisscrossing bright ice plains. The complete absence of impact craters told scientists that Europa's surface was geologically young. Somehow, this moon was renewing its face despite orbiting far from the sun's warmth. The dark lines etched across the surface look like frozen rivers or the patterns that form when thin ice breaks up on Earth's Arctic seas. Similarly, when Voyager 2 photographed Saturn's small moon Enceladus in 1981, it revealed a world split between ancient, heavily cratered terrain and smooth, crater-free regions that gleamed like fresh snow. The contrast was so stark, it looked like two different moons had been welded together. Some areas showed no impact, craters at all, suggesting that active processes had erased them within the last few million years. The explanation for these mysterious surfaces would revolutionize our understanding of where life might exist in the solar system. Both moons experience the same tidal heating that tortures Io, but at a gentler level. Their elliptical orbits around their parent planets create gravitational flexing that generates just enough heat to melt ice into liquid water. This is not the violent volcanism of Io, but a more subtle warming that can maintain oceans beneath protective ice crusts. Think of these moons as cosmic thermoses. The ice shells, averaging 10 to 15 miles thick, insulate the liquid water beneath from the frigid vacuum of space, where temperatures plunge to negative 300 degrees Fahrenheit. Meanwhile, tidal heating from the giant planets keeps the water from freezing solid, maintaining vast oceans that may contain more water than all of Earth's seas combined. Europa's ocean, hidden beneath its icy shell, likely contains twice as much water as all the oceans on Earth. The moon's ice crust acts like the Arctic ice pack, constantly breaking apart and refreezing as the liquid ocean beneath moves and churns. The dark lines crisscrossing Europa's surface are cracks where this process has exposed darker material from below or allowed fresh ice to well up and freeze. Enceladus harbors an even more remarkable secret. Its smooth southern regions suggested active geology that wouldn't be confirmed until later missions. But Voyager's images provided the first hints that this small moon was more than just a frozen ice ball. The geological activity, implied that liquid water could exist just beneath the surface, perhaps even occasionally breaking through to create temporary springs or geysers. These discoveries fundamentally changed how scientists think about habitability in the solar system. Life on Earth requires liquid water, and for decades, researchers assumed that meant planets had to orbit within a narrow, habitable zone around their stars. Not too hot, not too cold. But Europa and Enceladus proved that liquid water could exist almost anywhere, heated by gravitational forces rather than starlight. The implications staggered astrobiologists. If moons orbiting giant planets could maintain oceans for billions of years, then the number of potentially habitable worlds in our galaxy might be thousands of times larger than anyone had imagined. But the violent weather patterns discovered on the giant planets themselves were about to reveal just how extreme planetary systems could become. When Voyager 2 approached Neptune in August 1989, it discovered the most violent winds in the entire solar system, screaming across a world that should have been frozen into stillness. Neptune orbits 30 times farther from the Sun than Earth does, receiving only 1/10,000th as much solar energy. At that distance, the Sun appears as little more than a bright star in the sky. Logic suggested that Neptune should be a quiet, frigid world with barely any atmospheric activity. Instead, Voyager 2's instruments detected wind speeds reaching 1,500 miles per hour, nearly twice the speed of sound, and fast enough to circle Earth's equator in less than 17 hours. These aren't gentle breezes, but supersonic rivers of gas that make Earth's most devastating hurricanes look like summer zephyrs. The fastest winds ever recorded on Earth peaked at just over 300 miles per hour during extreme tornadoes. Neptune's atmosphere routinely generates winds 5 times more powerful, sustained across storm systems larger than our entire planet. What makes Neptune's winds even more mysterious is their direction. On Earth, the Sun heats tropical regions more than polar areas, creating temperature differences that drive our weather. Neptune receives such feeble sunlight that temperature differences between its equator and poles amount to only a few degrees. Yet somehow, this minimal energy input drives atmospheric circulation more violent than anything in our solar system. The answer lies in Neptune's internal heat engine. Like Jupiter, Neptune generates more energy than it receives from the Sun. In fact, it produces 2.5 times as much heat internally as solar heating provides. The planet's core burns at temperatures around 4,000 degrees Fahrenheit, creating powerful convection currents that rise through thousands of miles of hydrogen and helium atmosphere. But here is what makes Neptune's winds truly bizarre. They blow in the wrong direction. Most planets rotate faster at their equators than at their poles due to centrifugal force, and their fastest winds typically blow in the same direction as rotation. Neptune's winds do the opposite. They race backward against the planet's rotation, like rivers flowing uphill. Voyager 2 discovered enormous storm systems churning in Neptune's atmosphere, including the Great Dark Spot, an anticyclonic storm system comparable in size to Jupiter's Great Red Spot. But unlike Jupiter's centuries-old storms, Neptune's weather changes rapidly. The Great Dark Spot observed by Voyager 2 had completely vanished when the Hubble Space Telescope examined Neptune a few years later. The spacecraft's instruments revealed that Neptune's atmosphere consists of about 80% hydrogen, 19% helium, and traces of methane that give the planet its distinctive blue color. The methane absorbs red light from the Sun, allowing only blue wavelengths to reflect back to space. But methane can only remain liquid or gaseous under extreme pressure at Neptune's distance from the Sun. It should freeze solid. The combination of intense internal heating and minimal solar input creates a unique atmospheric laboratory where conventional weather patterns break down completely. Neptune essentially powers its own weather system, like a giant atmospheric engine, converting heat from its interior into kinetic energy that drives winds faster than most spacecraft travel. These impossible winds proved that planetary atmospheres could operate under principles completely different from Earth's familiar weather patterns. But the discoveries awaiting in Saturn's system would reveal even more complex interactions between planets and their families of moons. Voyager 1's cameras revealed Saturn's rings in unprecedented detail and discovered something that changed our understanding of how cosmic debris organizes itself. Tiny moons acting like gravitational traffic cops. Saturn's ring system spans over 175,000 miles from edge to edge, but measures less than 30 feet thick in most places, proportionally thinner than a sheet of paper. Scientists had assumed these rings formed from random collisions and gravitational forces, creating relatively smooth, uniform structures. Instead, Voyager found rings with sharp edges, gaps, spokes, braids, and structures that seemed to defy the basic laws of orbital mechanics. The biggest surprise was the F-ring, a narrow band of particles orbiting just beyond Saturn's main ring system. This ring appeared to be braided like hair, with strands weaving in and out of each other in complex patterns that should have been impossible. Gravitational forces should smooth out such structures within a few orbital periods. Yet, the F-ring maintained its intricate braided appearance like a cosmic rope, frozen in space. The solution to this mystery came when Voyager discovered two small moons, Prometheus and Pandora, orbiting on either side of the F-ring. These shepherd moons use their gravity to keep the ring particles corralled within a narrow band, preventing them from spreading outward or spiraling inward toward Saturn. Prometheus, the inner shepherd, speeds up ring particles that drift too close, boosting them to higher orbits. Pandora, the outer shepherd, slows down particles that wander too far out, causing them to fall back toward the ring. Think of these shepherd moons like cosmic cowboys herding cattle. Any ring particle that strays from the main herd gets nudged back into line by the gravitational influence of one of the shepherds. This process happens continuously, creating the braided structures as the shepherd's orbital periods slightly differ from the ring particles, causing them to lap each other repeatedly. But the F-ring's behavior gets even stranger. Voyager's images show dark spokes appearing and disappearing in Saturn's main rings, like the spokes of a ghostly bicycle wheel. These features rotated with Saturn's magnetic field rather than following the orbital motion of ring particles. This should be impossible since ring particles are made of ice and rock, not electrically charged material. The discovery of shepherd moons revolutionized our understanding of ring dynamics throughout the solar system. Similar gravitational shepherding creates the gaps in Saturn's rings, maintains the sharp edges of Uranus's rings, and even influences the structure of planetary ring systems around distant gas giants. The process requires incredible precision. The shepherd moons must maintain exactly the right orbital positions and sizes to keep their charges in line. Even more remarkable, some of Saturn's rings show evidence of being much younger than the planet itself. The gravitational shepherding process slowly drains energy from both the rings and the shepherd moons, suggesting that current ring systems may have formed within the last few 100 million years when comets or small moons broke apart near Saturn. Voyager also revealed that Saturn's rings contain billions of individual particles, ranging from tiny ice crystals to house-sized chunks, all orbiting Saturn like a miniature solar system. The ring particles closest to Saturn complete an orbit in just 7 hours, while those at the outer edge take 14 hours. creating complex resonances and interactions that sculpt the overall ring structure. These discoveries showed that planetary rings aren't static decorations, but dynamic, evolving systems where gravitational forces create order from chaos. But the most puzzling mystery in the outer solar system was yet to be solved, one that would baffle scientists for decades. Something was slowing down Pioneer 10 and Pioneer 11, and nobody could figure out what force was acting on these spacecraft as they traveled toward the stars. By the late 1990s, careful tracking of the Pioneer spacecraft revealed they were falling behind their predicted positions by about 240 miles, 400 kilometers, per year, a tiny discrepancy that grew larger with each passing year. The spacecraft were decelerating as if some invisible force was gently but constantly pulling them back toward the sun. This became known as the Pioneer anomaly, and it threatened to undermine our understanding of gravity itself. The mystery deepened because no known force could account for this deceleration. The spacecraft were far beyond the gravitational influence of any planet. Solar radiation pressure should push them away from the sun, not slow them down, even accounting for every possible source of drag or interference. The Pioneers were moving too slowly compared to what Einstein's equations predicted. Scientists proposed increasingly exotic explanations. Maybe the law of gravity worked differently at the edge of the solar system. Perhaps dark matter, that mysterious substance thought to make up most of the universe, was concentrated in our region of space and creating drag on the spacecraft. Some theorists suggested the Pioneers had encountered a new fundamental force of nature, or were being influenced by extra dimensions predicted by advanced physics theories. The implications were staggering. If gravity behaved differently than expected at large distances, it could explain why galaxies rotate faster than they should, and why the universe's expansion seems to be accelerating. The Pioneer anomaly might provide the first direct evidence for new physics beyond our current understanding of space, time, and matter. Think of it like discovering that a car consistently gets worse gas mileage on long trips than short ones, even when driving under identical conditions. Either something about cars fundamentally changes over distance, or some undetected force is acting on them during extended travel. The Pioneer anomaly presented the same puzzle on a cosmic scale. NASA ground controllers checked and rechecked their calculations. They accounted for every possible source of error: computer glitches, measurement uncertainties, relativistic effects, even the influence of charged particles from the solar wind. Nothing could explain why both Pioneer spacecraft were experiencing identical, constant deceleration of about 300 billion times smaller than Earth's gravity, but perfectly steady over decades of observations. The mystery persisted for over 30 years, spawning hundreds of scientific papers and inspiring entire conferences dedicated to understanding the anomaly. Some scientists built careers trying to solve it. Others used the Pioneer data to challenge fundamental assumptions about physics and cosmology. The breakthrough came when researchers realized they needed to account for heat radiation from the spacecraft themselves. Both Pioneers carried nuclear power sources that generated electricity by converting radioactive decay into heat. This heat had to go somewhere, and even tiny imbalances in how that heat radiated into space could create thrust. This is like holding a flashlight in space and being pushed backward by the light it emits. Detailed thermal modeling finally showed that the Pioneer's anomalous deceleration matched perfectly with the recoil force created by heat radiating unevenly from their nuclear power sources and internal electronics. The mystery force wasn't exotic physics, but simple thermodynamics, acting on spacecraft that weren't designed with perfect thermal symmetry. The solution to the Pioneer anomaly prove that even tiny, overlooked effects can masquerade as revolutionary discoveries in the precision world of space exploration. But as these early interstellar messengers continued their journeys, new spacecraft would reach more distant worlds and uncover phenomena that truly did rewrite the textbooks. New Horizons defied every expectation about Pluto when it revealed not a cold, dead rock, but a world more geologically active than Earth's moon. The first detailed images from New Horizons in July 2015 showed a heart-shaped region on Pluto's surface that immediately captured global focus. This feature, later named Tombaugh Regio, after Pluto's discoverer, spans about 900 miles across, roughly the distance from New York to Atlanta. But this wasn't just a pretty pattern on a distant world. The heart represented something scientists thought impossible: active geology on a dwarf planet smaller than Earth's moon, orbiting 39 times farther from the Sun. The western lobe of Pluto's heart consists of a vast plain of frozen nitrogen called Sputnik Planitia. It is completely free of impact craters, despite being exposed to 4.5 billion years of cosmic bombardment. On a dead world, craters should accumulate like scars on aged skin. Their absence meant that something was constantly renewing Pluto's surface, erasing the evidence of meteor impacts. New Horizons revealed the mechanism behind this geological activity: convection cells in the nitrogen ice sheet that work like a cosmic lava lamp. Radioactive decay in Pluto's rocky core generates just enough heat to keep the bottom of the nitrogen ice layer slightly warmer than the surface. This creates enormous convection cells, where warmer nitrogen rises from below while colder nitrogen sinks, constantly churning the surface and erasing impact craters. Each convection cell spans about 12 miles across and takes roughly 500,000 years to complete one cycle. This is incredibly slow by Earth standards, but remarkably fast for a world so distant and cold. The process creates a polygonal pattern visible in New Horizons images that looks like frozen honeycombs stretched across an area larger than Texas. But Pluto's geological surprises didn't stop with nitrogen glaciers. The spacecraft discovered mountain ranges made of water ice that rise over 11,000 feet above the surrounding plains, taller than Mount Hood in Oregon. These mountains formed through processes similar to those that created Earth's mountains, but using water ice instead of rock. At Pluto's frigid temperatures, water ice becomes as hard as granite and can support mountain ranges for billions of years. Even more remarkable, New Horizons found evidence of recent volcanic activity on Pluto. These are not eruptions of molten rock, but cryovolcanoes that spew liquid nitrogen, water, and ammonia mixtures. These ice volcanoes create smooth, young surfaces that show the dwarf planet remained geologically active within the last few million years, possibly continuing to the present day. The spacecraft also revealed that Pluto experiences seasons despite its incredible distance from the Sun. The dwarf planet's elliptical orbit and tilted axis create temperature changes that cause its thin atmosphere to expand and contract dramatically over its 248-year orbital period. During Pluto's brief summer, nitrogen ice sublimes from the surface directly into gas, creating weather patterns, including possible nitrogen snow. Perhaps most surprising of all, New Horizons discovered that Pluto may harbor a subsurface ocean of liquid water beneath its frozen surface. The gravitational interactions between Pluto and its large moon Charon, combined with radioactive heating, could maintain pockets of liquid water for billions of years. This raises the tantalizing possibility that even worlds at the frigid edge of the solar system might maintain the basic ingredients necessary for life. Pluto's dynamic geology, proved that size and distance from the sun don't automatically doom worlds to geological death. But the most profound discovery about our place in the cosmos came from a simple photograph taken as these spacecraft looked back toward home. On February 14, 1990, Voyager 1 turned its cameras backward toward home and captured an image that changed how humanity sees itself in the universe. The photograph showed Earth as a tiny blue dot suspended in a sunbeam, occupying less than 1 pixel in the vast darkness of space. From Voyager's position over 4 billion miles away, our entire world appeared smaller than a grain of sand viewed from across a football field. Every human who had ever lived, every civilization that had ever risen and fallen, every war fought and peace treaty signed, all of it existed on that barely visible speck of light. This image, later dubbed the pale blue dot by Carl Sagan, represented the most distant photograph ever taken of Earth at the time. Voyager 1 had traveled farther from home than any human creation before it, reaching a distance where Earth no longer dominated the sky, but became just another point of light among countless others scattered across the cosmic dark. The photograph almost didn't happen. NASA engineers worried about pointing Voyager's cameras back toward the sun, fearing that the intense solar radiation might damage the instruments. The spacecraft's cameras had been designed to photograph the outer planets, not to look back at the inner solar system, where the sun's glare could overwhelm their sensitive detectors. But Carl Sagan, the planetary scientist who had championed messages to alien civilizations on both Voyager spacecraft, convinced NASA to attempt the solar system family portrait. On Valentine's Day, 1990, Voyager 1 obediently turned around and began photographing the sun and planets from its unique vantage point beyond Neptune's orbit. The resulting images revealed our solar system as we had never seen it before. From the outside, looking in, 6 planets appeared in the mosaic of 60 photographs: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was lost in the sun's glare, while Mars was too dark to detect. Of all the worlds visible in these images, only Earth showed the distinctive blue color that marks it as a planet with liquid water, oceans, and an oxygen-rich atmosphere. The pale blue dot occupied just 0.12 pixels in the image, a cosmic mote of dust caught in a scattered sunbeam. No continents, no clouds, no signs of the teeming life that makes Earth unique in the known universe. From Voyager's perspective, our world looked utterly insignificant, indistinguishable from countless other points of light scattered across the galaxy. Yet, this tiny dot contained everything humans had ever known or cared about. Every person who had ever lived out their hopes and dreams. Every species that had evolved over billions of years. Every mountain range and ocean and forest. All confined to that barely visible speck suspended in the cosmic dark. The photograph served as a profound reminder of Earth's fragility and isolation. There is no other refuge for human civilization, no backup planet waiting in our solar system. The nearest potentially habitable worlds orbit other stars trillions of miles away, utterly unreachable with current technology. For the foreseeable future, that pale blue dot represents the only home humanity will ever know. Carl Sagan later wrote that the image underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. From the edge of the solar system, all human conflicts and territorial disputes seemed petty and meaningless compared to the vast emptiness that surrounds our tiny world. The pale blue dot photograph marked the end of an era when humans could imagine Earth as the center of creation. But as our robotic explorers ventured even deeper into space, They would discover that the journey between worlds required navigating hazards no one had anticipated. Pioneer 10 became the first spacecraft to attempt passage through the asteroid belt in 1972, and nobody knew if it would survive the journey. Science fiction movies portrayed asteroid belts as chaotic minefields, where spaceships had to dodge house-sized rocks while weaving through fields of cosmic debris. Scientists worried that Pioneer 10 might be battered to death by high-speed impacts as it crossed the belt between Mars and Jupiter. Some estimates suggested the spacecraft had only a 50-50 chance of making it through intact. The asteroid belt spans roughly 175 million miles, 3 times the distance from Earth to the Sun, and contains millions of rocky fragments, ranging from pebbles to objects hundreds of miles across. These asteroids race through space at speeds up to 45,000 miles per hour, carrying enough kinetic energy to vaporize any spacecraft unlucky enough to collide with them. But when Pioneer 10 crossed into the belt on February 15, 1973, it discovered something completely unexpected. The asteroid belt was mostly empty space. Despite containing millions of individual objects, the belt proved so sparse that Pioneer encountered virtually no debris during its passage. The total mass of all asteroids combined equals less than 5% of Earth's moon, spread across a volume of space larger than the orbit of Mars. Think of the asteroid belt like a massive parking lot the size of Texas, with only a few dozen cars scattered randomly across it. From any given point, you could look in every direction and see nothing but empty space stretching to the horizon. The chances of randomly encountering an asteroid during a straight-line passage through the belt were astronomically small, literally less than 1 in a billion. Pioneer's instruments detected only a slight increase in cosmic dust during the belt crossing, mostly particles smaller than grains of sand. The spacecraft suffered no significant impacts and experienced no damage to its systems. What had seemed like a treacherous obstacle course turned out to be a relatively safe highway through the inner solar system. This discovery revolutionized mission planning for future spacecraft. If Pioneer could cross the asteroid belt safely, then so could Voyager, Galileo, Cassini, and dozens of other probes destined for the outer planets. The belt represented not a barrier to exploration, but a cosmic superhighway connecting the inner and outer solar systems. The emptiness of the asteroid belt also revealed important clues about the formation of our solar system. The asteroids represent leftover building blocks from planetary formation 4.5 billion years ago, material that never accumulated into a full-size planet due to gravitational disruption from nearby Jupiter. If this debris had remained densely packed, it would have eventually coalesced into a rocky world between Mars and Jupiter. Instead, Jupiter's massive gravity stirred up the asteroid orbits, causing frequent high-speed collisions that shattered larger objects, rather than allowing them to grow. Over billions of years, most of the original asteroid material either crashed into existing planets, got ejected from the solar system entirely, or ground itself down into dust that spiraled into the sun. Pioneer's safe passage proved that space exploration required rethinking many assumptions about the dangers lurking between worlds. The greatest hazard wasn't asteroid impacts, but the gradual accumulation of cosmic dust and radiation exposure during years-long journeys to distant planets. The asteroid belt discovery also confirmed that spacecraft could navigate the solar system along predictable routes, opening up the entire outer solar system for detailed exploration. But as these robotic ambassadors continued their journeys, they carried with them humanity's first attempts to communicate with alien intelligences, who might someday find them drifting between the stars. Bolted to the antenna supports of Pioneer 10 and Pioneer 11, two 6-inch by 9-inch golden plaques carry humanity's first message designed for alien eyes. The idea came from Carl Sagan after he realized that both Pioneer spacecraft would eventually drift into interstellar space, potentially outlasting human civilization itself. If alien explorers ever discovered these ancient probes millions of years in the future, they would find humanity's first attempt to say hello to the cosmos. A cosmic note in a bottle cast into the vast ocean between stars. The plaques feature line drawings of a nude human male and female standing in front of an outline of the Pioneer spacecraft for scale reference. The man's hand is raised in a gesture of peace. Though the designers worried that aliens might interpret any gesture as threatening or meaningless, they chose to show humans without clothing. This was done to avoid depicting temporary fashion choices that might confuse extraterrestrial archaeologists trying to understand human biology. But the real ingenuity lies in the scientific information etched alongside the human figures. The plaques include a map showing Earth's location relative to 14 pulsars, spinning neutron stars that emit regular radio beams like cosmic lighthouses. Since pulsars slow down at predictable rates over millions of years, aliens could use this information to determine both where the spacecraft came from and when it was launched. Think of the pulsar map like a cosmic GPS system, readable by any scientifically advanced civilization. The lines radiating from Earth point toward different pulsars, with symbols indicating each pulsar's spin rate and distance. Even if human civilization vanishes, these cosmic beacons will continue broadcasting their regular signals for millions of years, providing permanent navigational landmarks that aliens could use to find Earth. The plaques also include diagrams showing the hyperfine transition of hydrogen atoms, the most common element in the universe. This scientific information serves as a universal measuring stick that any civilization capable of interstellar travel should understand. By defining time and distance in terms of hydrogen's fundamental properties, the plaques provide a translation key for all other measurements shown on the message. Creating the messages required solving unprecedented communication challenges. How do you explain human anatomy, Earth's location, and the spacecraft's origin to minds that might think in completely alien ways? The designers assumed that any civilization capable of finding and examining the Pioneer probes would necessarily understand mathematics, physics, and astronomy, the universal languages of science. The golden anodized aluminum plaques were designed to survive for millions of years in the harsh environment of interstellar space. Gold plating protects the etched aluminum from corrosion by cosmic rays and interstellar dust. The plaques are mounted where the spacecraft's body shields them from most impacts, while keeping them visible to any intelligence that might encounter the probes. Both Pioneer 10 and Pioneer 11 carry identical plaques, doubling the chances that humanity's first interstellar message will eventually be found. Pioneer 10 heads toward the constellation Taurus and will pass near the star Aldebaran in about 2 million years. Pioneer 11 travels toward Aquila and will encounter nearby stars in roughly 4 million years. The plaques represent humanity's earliest attempt to think beyond our own species and planet. They forced us to consider how we might appear to alien intelligences and what aspects of human civilization deserved preservation for cosmic posterity. In many ways, designing these messages revealed as much about human nature as they communicated about it. The Pioneer plaques established a tradition that continues today. The idea that our spacecraft should carry information about their creators into the unknown. But future missions would carry far more elaborate messages, including sounds and images that painted richer portraits of life on Earth. On New Year's Day 2019, New Horizons flew past the most ancient and pristine object humans had ever examined, a frozen relic from the birth of the solar system itself. Arakoth, officially designated 2014 MU-69, orbits in the Kuiper Belt over 4 billion miles from the Sun. At that tremendous distance, the object has remained virtually unchanged since the solar system formed 4.5 billion years ago. Unlike planets and moons that have been heated, melted, and reshaped by geological processes, Arakoth preserves the original materials and structure of the primordial disk from which all worlds formed. The spacecraft revealed an object unlike anything previously seen. 2 lobes connected by a narrow neck, resembling a cosmic snowman or spinning dumbbell about 21 miles long. The unusual shape immediately told scientists that Arakoth formed through a gentle process rather than violent collisions. The 2 lobes originally formed as separate objects that slowly spiraled together and merged at walking speed, never generating enough heat to melt or significantly alter their internal structure. This discovery revolutionized our understanding of how planets form. Traditional theories suggested that planetary building blocks grew through high-speed collisions that gradually built larger objects through accretion. Arakoth's pristine condition and gentle binary structure proved that at least some building blocks formed through gravitational instabilities in the early solar nebula. This was a much calmer process that preserved primitive materials in their original state. New Horizons images showed Arakoth's surface covered in small hills and pits, but completely lacking the large impact craters that scar most solar system objects. The absence of major craters confirmed that the Kuiper Belt remains a relatively quiet neighborhood where ancient objects can survive unchanged for billions of years. Any large impacts would have shattered Arakoth's fragile structure long ago. The color measurements revealed additional secrets about solar system formation. Arakoth appears reddish-brown due to organic compounds created by billions of years of radiation exposure. These same organic materials likely existed throughout the early solar system and may have provided the raw ingredients for life when they were delivered to Earth and other planets by comets and asteroids. Even more remarkable, New Horizons detected no signs of water ice on Arakoth's surface, despite the object forming in the cold outer reaches of the solar nebula. This suggests that water, ice, and rock materials were separated into different regions during planetary formation, a process that helped determine which worlds would become rocky planets like Earth versus icy bodies like comets. The spacecraft's instruments also revealed that Arakoth rotates once every 15.5 hours, tumbling end over end like a slow-motion football. The rotation axis remains stable, indicating that the object hasn't suffered any major impacts that would have altered its spin. This stable rotation preserves information about the original angular momentum of the materials from which Arakoth formed. Perhaps most importantly, Arakoth represents the first Kuiper Belt object examined up close by a spacecraft. The Kuiper Belt contains thousands of similar objects, a vast repository of primitive materials that record conditions in the outer solar system during planetary formation. Each of these frozen time capsules preserves slightly different information about the processes that shaped our cosmic neighborhood. New Horizons demonstrated that reaching these ancient objects requires incredible precision and patience. The spacecraft had to travel for over 13 years and cover more than 4 billion miles to reach its target, which appeared as nothing more than a moving dot of light in Earth's most powerful telescopes. The flyby itself lasted only a few hours, but it provided humanity's first detailed look at the raw materials from which entire worlds were built. But as New Horizons continued its journey deeper into the Kuiper Belt, it began encountering the first signs of the boundary where our sun's influence starts to weaken. A cosmic frontier that would test every spacecraft brave enough to cross it. New Horizons approaches the first of several invisible barriers that mark the edge of our sun's protective domain. A cosmic battlefield where solar particles crash into the interstellar medium. The termination shock represents one of the most dramatic boundaries in the solar system, though it remains completely invisible to human eyes. Here, the solar wind, that constant stream of charged particles blasting outward from the sun at over 1 million miles per hour, suddenly slams into interstellar matter and drops to subsonic speeds. The collision creates a shock wave that extends across billions of miles, forming a vast spherical front, advancing ahead of our entire solar system as it moves through the galaxy. Think of our solar system as a speedboat racing across a lake. The boat creates a wake and a bow wave that pushes water aside as it moves forward. The termination shock is like that bow wave, except instead of water, it's made of colliding streams of charged particles, heated to temperatures of millions of degrees. The shock region spans hundreds of millions of miles and creates some of the most extreme plasma conditions found anywhere in nature. New Horizons will likely encounter this boundary sometime in the late 2020s, becoming only the third spacecraft to cross the termination shock after Voyager 1 and Voyager 2. But New Horizons carries more advanced instruments than the aging Voyager probes, offering scientists their best opportunity to study this cosmic frontier with modern technology. The termination shock marks where the sun's authority begins to weaken, but hasn't yet ended. Beyond this boundary lies the heliosheath, a turbulent region where the solar wind continues to flow outward, but at much slower speeds, gradually mixing with interstellar particles. This mixing zone extends for billions more miles before reaching the heliopause, where the sun's influence finally ends and true interstellar space begins. What makes the termination shock particularly interesting is how it accelerates particles to incredible energies. When solar wind particles slam into this barrier, some get reflected back toward the inner solar system, while others are accelerated to nearly the speed of light. These high-energy particles contribute to the cosmic ray background that bathes our entire solar system, including Earth. The shock boundary constantly moves and fluctuates as the sun's activity changes over its 11-year cycle. During periods of high solar activity, increased solar wind pressure pushes the termination shock farther from the sun. During quiet periods, the boundary moves inward. These movements can span tens of millions of miles, making the shock more like a breathing boundary than a fixed wall. Voyager 1 crossed the termination shock at about 85 astronomical units, AU, from the Sun in December 2004, while Voyager 2 encountered it at 84 AU in August 2007. The slight difference in distances reflected the shock's irregular shape, as it responds to variations in solar wind strength and local interstellar conditions. New Horizons will approach the termination shock from a different angle than the Voyager probes, providing scientists with their first three-dimensional view of this cosmic boundary. The spacecraft's modern instruments can measure particle energies, magnetic fields, and plasma conditions with far greater precision than the pioneering voyages achieved decades ago. The data from New Horizons' termination shock encounter will help scientists understand how our solar system interacts with the broader galaxy and how similar boundaries might exist around other star systems throughout the universe. But crossing this first barrier will only mark the beginning of New Horizons' journey into the unknown regions that surround our cosmic neighborhood. New Horizons detected more cosmic dust impacts than any computer model predicted, suggesting our solar system contains far more debris than we ever imagined. The spacecraft carries a student-built dust counter that measures particles smaller than grains of sand as they strike its detectors at speeds reaching 45,000 miles per hour. Each impact creates a tiny flash of light and a voltage pulse that reveals the particle's mass and velocity. Scientists expected dust impacts to decrease steadily as New Horizons moved farther from the Sun, following the same pattern observed throughout the inner solar system. Instead, the dust counter registered consistently high impact rates, even as New Horizons traveled deeper into the Kuiper Belt. The spacecraft should have encountered a Kuiper cliff, where particle density drops dramatically beyond 50 astronomical units from the Sun. Ground-based telescopes had observed exactly this pattern. Fewer and fewer large objects visible at greater distances, suggesting the Kuiper Belt ends rather abruptly. But New Horizons dust measurements told a different story. The impact rate remains stubbornly high, indicating that microscopic debris continues far beyond the region, where large Kuiper Belt objects become scarce. Either our understanding of the Kuiper Belt structure was completely wrong, or New Horizons was detecting evidence of a previously unknown population of objects. Think of it like driving down a highway, where the number of cars gradually decreases, but the amount of roadside litter stays constant. The absence of large vehicles doesn't necessarily mean the road is empty. It might just indicate that smaller debris becomes the dominant population in that region. The discovery suggests that the Kuiper Belt may extend much farther into space than previously thought, possibly containing a second, more distant belt of debris left over from the solar system's formation. This extended belt could harbor millions of small objects, too distant and faint to detect from Earth, but numerous enough to create the steady rain of dust particles striking New Horizons. Alternative explanations include the possibility that interstellar dust is more abundant in our region of the galaxy than models predict. As our solar system moves through space at over 60,000 miles per hour, it plows through interstellar matter, like a ship moving through water. This could concentrate dust particles ahead of our solar system, creating higher impact rates than expected from Kuiper Belt debris alone. The dust measurements also revealed information about the age and composition of particles in the outer solar system. Many impacts showed characteristics of pristine materials that have remained unchanged since the solar system formed. Cosmic fossils that preserve information about conditions in the primordial disk from which planets grew. Each dust grain tells a story about its origin and history. Particles from comets contain different ratios of rock and ice than debris from asteroid collisions. Interstellar dust carries isotope signatures that reveal which stellar explosions created the heavy elements it contains. New Horizons essentially flies through a museum of cosmic archaeology, collecting samples of materials that span billions of years of solar system evolution. The extended Kuiper Belt discovery has profound implications for understanding how planetary systems form and evolve. If our solar system contains more debris than expected, similar, hidden populations might exist around other stars, affecting how planets develop and migrate within those systems. But the dust impacts represent just one type of information flowing back from New Horizons as it ventures into increasingly alien territory, where the basic properties of space itself begin to change. Beyond Neptune's orbit, New Horizons travels through a cosmic highway system that carries material between stars across distances that boggle the imagination. Every grain of dust striking the spacecraft tells a story of incredible journeys spanning millions of years and trillions of miles. Some particles formed in the atmospheres of dying stars, hundreds of light years away. Blown into space by stellar winds and carried along by the galaxy's rotation. Others were blasted from comets in distant solar systems, and now drift through the interstellar medium like cosmic tumbleweeds. The dust counter aboard New Horizons can distinguish between these different populations based on their speed, direction, and composition. Local debris from our own Kuiper Belt typically moves at relatively slow speeds and follows predictable orbital patterns around the Sun. Interstellar dust particles, however, race through our solar system at much higher velocities, sometimes exceeding 100,000 miles per hour, and arrive from directions that point toward other star systems. These measurements revealed that interstellar space is far from empty. The region between stars contains roughly 1 atom per cubic centimeter, along with countless microscopic dust grains, magnetic fields, and traces of organic molecules. While this density seems incredibly sparse compared to Earth's atmosphere, it represents a vast reservoir of material that influences how stars form and how galaxies evolve over cosmic time. Think of interstellar dust, like snow falling on a highway. Individual flakes seem insignificant, but over time they accumulate into drifts that can reshape the landscape. Similarly, interstellar dust gradually builds up in certain regions of the galaxy, eventually becoming dense enough to collapse under its own gravity and form new stars and planetary systems. New Horizons detected dust particles containing silicon, carbon, iron, and other heavy elements that could only have formed inside stars and been scattered into space when those stars died. Every impact represents material that was once part of a stellar furnace, billions of miles away, forged in nuclear reactions and expelled during supernova explosions or stellar winds. The spacecraft's measurements also revealed how our solar system's motion through the galaxy affects the dust environment in our neighborhood. As the Sun travels through space, it encounters different regions of interstellar matter, sometimes passing through relatively empty voids. Other times, crossing denser clouds of gas and dust that were expelled from nearby star-forming regions. These variations in interstellar density have important consequences for life on Earth. When our solar system passes through dense interstellar clouds, the increased pressure from outside can compress the heliosphere, our Sun's protective magnetic bubble. This compression allows more galactic cosmic rays to penetrate the inner solar system, potentially affecting Earth's climate and the evolution of life. The dust measurements from New Horizons provide the first direct sampling of interstellar material as our solar system moves through it. Previous studies relied on remote observations or analysis of interstellar particles captured by spacecraft in Earth's vicinity. New Horizons offers a real-time survey of cosmic dust conditions at the edge of our solar system. Each grain impact also carries information about the magnetic fields and radiation environment in interstellar space. The particles' trajectories reveal how galactic magnetic fields deflect and channel matter between stars, creating invisible highways that guide the flow of material across vast distances. Understanding these interstellar highways helps scientists predict what conditions New Horizons will encounter as it ventures even deeper into space, where the fundamental forces that shape our cosmic neighborhood begin to change in ways that challenge our most basic assumptions about physics. Voyager 1 detected something impossible as it crossed into interstellar space. The Sun's magnetic field refused to reverse direction the way every computer model predicted it should. For decades, scientists assumed that crossing the heliopause would be like passing through a magnetic membrane, separating two different realms. On the solar system side, magnetic field lines should point in directions determined by the Sun's rotation and activity. On the interstellar side, they should follow completely different orientations dictated by galactic processes operating on much larger scales. The boundary between these two magnetic domains should have been obvious, like crossing from a region where all compass needles point north into an area where they suddenly swing to point south. Voyager's magnetometer instruments were specifically designed to detect this dramatic field reversal as proof that the spacecraft had truly left the solar system behind. Instead, Voyager 1 found magnetic chaos that defied every theoretical prediction. The field strength changed dramatically as expected, but the direction remained stubbornly similar to what the probe had measured. While still inside the heliosphere, the magnetic field had apparently developed a case of cosmic amnesia, forgetting that it was supposed to flip direction when crossing into interstellar space. This discovery suggested that the boundary between solar and interstellar space is far more complex than a simple dividing line between two magnetic territories. Instead of a sharp transition, Voyager encountered a turbulent mixing zone where solar and galactic magnetic fields intertwine like twisted cables. The field lines don't simply reverse. They form complex, braided structures that can extend across millions of miles. Think of magnetic field lines like invisible highways that guide the motion of charged particles through space. Where different highway systems meet, you'd expect clear intersections and direction changes. Instead, Voyager found something resembling a massive traffic jam, where highways from different regions merge, split, and reconnect in bewildering patterns. The magnetic complexity arises because interstellar space isn't uniform. Our solar system moves through regions of varying density and magnetic strength as it orbits the galaxy. Sometimes we pass through relatively empty voids where galactic magnetic fields are weak. Other times, we encounter denser clouds where strong magnetic fields have been amplified by compression or twisted by turbulence. Voyager 2, following a different trajectory through space, encountered similar magnetic confusion when it crossed the heliopause 6 years later. Both spacecraft found that interstellar magnetic fields near our solar system happened to run roughly parallel to the Sun's field, creating the illusion that nothing had changed, even though the spacecraft had definitely entered a completely different magnetic domain. The implications of this discovery extend far beyond our local cosmic neighborhood. If magnetic fields don't behave predictably at the boundaries between stellar and interstellar space, then our understanding of how charged particles move through the galaxy may be fundamentally flawed. This could affect theories about cosmic ray propagation, star formation, and the evolution of magnetic fields in spiral galaxies. The magnetic field measurements also revealed that the heliopause itself moves and fluctuates over timescales ranging from days to decades. Solar activity changes the strength and extent of our magnetic bubble, while variations in interstellar pressure cause the boundary to breathe in and out like a cosmic lung. These discoveries showed that the edge of our solar system resembles a dynamic weather front rather than a fixed boundary, with magnetic storms and field reversals occurring on scales that dwarf any terrestrial magnetic phenomena. But as our distant scouts continue their journeys into this magnetic wilderness, they encounter temperature conditions that approach the ultimate limit of cold that physics allows. In the vast emptiness between stars, our most distant spacecraft encounter cold so extreme, it approaches the theoretical limit where all atomic motion ceases forever. The temperature of interstellar space averages around 3 Kelvin, about negative 454 degrees Fahrenheit, just degrees above absolute zero. At these temperatures, the few atoms scattered through space move so slowly they barely qualify as matter in any meaningful sense. If you could somehow transport a cup of water to interstellar space, it would freeze solid in microseconds and then continue cooling until the ice became harder than steel. Voyager 1's instruments measured this cosmic deep freeze as the spacecraft crossed from the relatively warm environment inside our solar system's heliosphere into the frigid interstellar medium. The temperature difference seems small in absolute terms, only a few degrees, but it represents crossing a fundamental threshold where the physics of matter begins to behave in strange ways. Think of interstellar space as nature's ultimate refrigerator, one that has been cooling down for over 13 billion years since the universe began expanding after the Big Bang. The only heat sources in this cosmic freezer are the faint radiation left over from creation itself and the occasional energy released when sparse interstellar atoms collide with each other at incredibly slow speeds. At these extreme temperatures, ordinary matter enters quantum mechanical states that don't exist under normal conditions. Individual atoms can occupy the same quantum state simultaneously, creating exotic forms of matter, like Bose-Einstein condensates that behave more like waves than particles. These quantum effects only become noticeable when thermal motion drops to nearly zero. The cold of interstellar space makes even the darkest winter on Earth seem tropical by comparison. The coldest natural temperature ever recorded on Earth was minus 128.6 degrees Fahrenheit in Antarctica. Interstellar space is over 300 degrees colder than that, approaching the absolute zero point, where all thermal motion would cease entirely if perfect conditions existed. But perfect absolute zero remains impossible to achieve anywhere in the universe because quantum mechanics prevents particles from ever becoming completely motionless. Even in the deepest cold of intergalactic space, atoms retain tiny amounts of motion called zero-point energy that keeps them vibrating at the smallest possible level allowed by the laws of physics. The extreme cold affects how our spacecraft operate in ways their designers never fully anticipated. Electronic circuits that worked perfectly at room temperature, or even in the cold vacuum near Earth, begin behaving unpredictably as they approach these cosmic temperature extremes. Metal components contract and become brittle. Lubricants and moving parts freeze into solid blocks. Most remarkably, the cold of interstellar space actually helps preserve our distant spacecraft for far longer than anyone expected. Chemical reactions that cause corrosion and degradation slow to nearly imperceptible rates at these temperatures. Materials that would decompose quickly on Earth could potentially remain intact for millions of years in the cosmic deep freeze. New Horizons and the Voyager probes essentially function as time capsules that will remain frozen in their current state long after human civilization evolves into something unrecognizable. The extreme cold acts like a natural preservative, protecting our first interstellar emissaries from decay as they drift through the galaxy. The temperature measurements from these distant explorers also provide crucial data for understanding how heat flows through the galaxy and how the universe itself continues to cool as it expands. Each degree of cosmic cold represents billions of years of expansion and cooling since the hot, dense conditions that existed moments after the Big Bang. But while the universe grows colder with each passing eon, one spacecraft follows a unique path that reveals hidden aspects of our solar system structure, invisible from any other vantage point. Alone among humanity's interstellar ambassadors, Voyager 2 follows a path that carries it below the plane of the solar system, revealing a completely different view of our cosmic neighborhood. After completing its grand tour of the outer planets, Voyager 2's encounter with Neptune in 1989 sent the spacecraft diving southward at a steep angle relative to the disk where planets orbit. This trajectory makes Voyager 2 unique among the 5 spacecraft leaving our solar system. All the others travel roughly within the same flat plane that contains Earth, Mars, Jupiter, and the other planets. Think of the solar system as a giant dinner plate with the Sun at the center and all the planets arranged around the rim. Most of our interstellar spacecraft skim along the surface of this plate as they head toward deep space. Voyager 2, however, plunges underneath the plate, providing humanity's only view of what lies below our familiar solar system plane. This southern trajectory revealed that the heliosphere, our Sun's protective magnetic bubble, has a distinctly lopsided shape rather than the perfect sphere that scientists had expected. Voyager 2 crossed into interstellar space at a different distance from the Sun than Voyager 1, confirming that the boundary between solar and interstellar space varies dramatically depending on direction. The asymmetry arises because our entire solar system is moving through the galaxy at over 60,000 miles per hour, plowing through interstellar matter like a boat cutting through water. This motion compresses the heliosphere in the direction we're traveling, while stretching it out behind us like a cosmic teardrop. Voyager 2's unique vantage point revealed the shape of this teardrop from below, showing how interstellar pressure sculpts our protective bubble. From its southern perspective, Voyager 2 also detected differences in the galactic cosmic ray environment that surrounds our solar system. These high-energy particles, created by exploding stars throughout the galaxy, approach our solar system from all directions, but with varying intensities that depend on the local magnetic field structure and the density of interstellar matter. The spacecraft's southern trajectory carries it toward regions of space that ground-based telescopes cannot easily observe. Most astronomical observations focus on objects visible from Earth's northern hemisphere, leaving vast areas of the southern sky less thoroughly explored. Voyager 2 ventures into these relatively unknown territories, serving as humanity's scout in cosmic regions we've barely begun to study. The probe's unique path also provides crucial data for understanding how our solar system interacts with the local interstellar cloud, a relatively dense region of gas and dust that our solar system has been passing through for the past 100,000 years. This cloud affects the shape and size of the heliosphere, and Voyager 2's measurements from below reveal how these interactions vary with direction. Perhaps most importantly, Voyager 2's southern trajectory offers a different perspective on the magnetic field structures that guide charged particles through interstellar space. The spacecraft encounters galactic magnetic field lines that run in different directions than those measured by Voyager 1, helping scientists construct a three-dimensional map of magnetic highways between the stars. The data from Voyager 2's southern journey will become increasingly valuable as the spacecraft ventures deeper into interstellar space. Its unique trajectory ensures that it will encounter different populations of interstellar matter and different magnetic field orientations than any other human-made object. This lone southern explorer also faces a different radiation environment than its northern companions. Galactic cosmic rays don't arrive uniformly from all directions. They're channeled and deflected by magnetic fields on scales spanning hundreds of light years. Voyager 2 samples this radiation environment from a completely different angle, providing insights into how cosmic rays propagate through our region of the galaxy. But regardless of direction, all our interstellar explorers face an increasingly hostile radiation environment. As they venture farther from the Sun's protective influence, beyond the heliosphere's protective boundary, our spacecraft face a radiation environment more hostile than anything encountered in Earth orbit. This is a constant bombardment of high-energy particles from exploding stars scattered across the galaxy. Galactic cosmic rays represent some of the most energetic phenomena in the universe. These particles race through interstellar space at nearly the speed of light, carrying energies millions of times greater than anything produced in Earth's most powerful particle accelerators. A single cosmic ray proton can pack as much energy as a baseball thrown by a major league pitcher, all concentrated into a space smaller than an atomic nucleus. Voyager 1's instruments detected a significant increase, 9%, in cosmic ray intensity when it crossed into interstellar space, confirming that our sun's heliosphere provides significant protection from galactic radiation. Inside the solar system's magnetic bubble, the solar wind creates a partial barrier that deflects many cosmic rays before they can reach the inner planets. Outside this protection, spacecraft face the full fury of radiation from stellar explosions that occurred millions of years ago. These cosmic rays originated in some of the most violent events in the galaxy, supernovae, where massive stars exploded with the force of billions of hydrogen bombs, detonating every second for months. The shockwaves from these stellar deaths accelerate nearby particles to incredible speeds, flinging them across interstellar space like cosmic bullets that travel for millions of years before reaching our solar system. Think of galactic cosmic rays as ancient messengers carrying news of stellar catastrophes from distant regions of the galaxy. Each particle began its journey when a star somewhere in our cosmic neighborhood reached the end of its life and exploded with enough force to outshine entire galaxies for brief moments. The radiation we detect today carries information about stellar deaths that occurred when dinosaurs ruled Earth. The cosmic ray environment varies dramatically, depending on where our solar system happens to be located as it orbits the galaxy. Sometimes we pass through relatively quiet regions where few nearby stars have exploded recently. Other times, we traverse areas still reverberating from recent supernovae, creating much higher radiation levels that can affect Earth's climate and the evolution of life. Our distant spacecraft serve as early warning systems for changes in the galactic radiation environment. As cosmic ray intensity increases or decreases, it affects everything from satellite operations to airline safety to the formation of clouds in Earth's atmosphere. The data from Voyager and New Horizons helps scientists predict these changes and understand their long-term effects on our planet. The radiation also poses significant challenges for the spacecraft themselves. High-energy cosmic rays can flip bits in computer memory, causing software glitches and instrument malfunctions. They gradually degrade electronic components, shortening the operational lifetime of systems that were designed to last for decades. Some cosmic ray impacts are energetic enough to permanently damage sensitive detectors. Even more concerning, cosmic rays create secondary radiation when they strike spacecraft materials. A single high-energy proton can shatter atomic nuclei in metal components, creating showers of radioactive fragments that continue to emit radiation long after the initial impact. This secondary radiation slowly accumulates inside the spacecraft, creating an increasingly hazardous environment for electronic systems. The cosmic ray measurements from our interstellar explorers also provide insights into fundamental physics under extreme conditions. These particles carry energies that cannot be reproduced in Earth-based laboratories, offering unique opportunities to study matter and energy at the limits of what nature allows. But as our spacecraft venture deeper into this radiation-soaked environment, they discover that the very boundaries of our solar system are more dynamic and fragile than anyone imagined. The magnetic shield that protects all life in our solar system from deadly galactic radiation is slowly weakening as our sun ages, and its influence over interstellar space begins to fade. Our sun creates the heliosphere by constantly blasting charged particles into space at over 1 million miles per hour. This solar wind inflates a vast magnetic bubble around our entire solar system, extending far beyond the orbit of Pluto. and pushing back against the hostile radiation environment of interstellar space. Without this protection, Earth would be bombarded by cosmic rays intense enough to strip away our atmosphere and sterilize the planet's surface. But the sun's power is not constant. Over its 11-year activity cycle, the solar wind varies in strength and density, causing the heliosphere to expand and contract like a breathing organism. During periods of high solar activity, increased particle output inflates the protective bubble farther into space. During quiet periods, the heliosphere shrinks inward, allowing galactic cosmic rays to penetrate deeper into our solar system. Voyager measurements revealed that this cosmic breathing affects the entire structure of interstellar space around our solar system. When the heliosphere expands, it compresses nearby interstellar matter and strengthens local magnetic fields. When it contracts, the pressure decreases and allows interstellar material to flow closer to our planetary neighborhood. Even more concerning, the sun itself is gradually aging and losing the nuclear energy that powers the solar wind. Over billions of years, our star will slowly weaken as it exhausts the hydrogen fuel in its core. This process happens so gradually that it's imperceptible over human timescales, but it means the heliosphere will eventually shrink until it no longer provides adequate protection for life on Earth. The heliosphere's boundaries also fluctuate due to our solar system's motion through varying regions of interstellar space. As we orbit the galaxy, we sometimes pass through dense interstellar clouds that push back against the solar wind with increased pressure. Other times, we traverse empty voids where the heliosphere can expand farther into space with less resistance. Currently, our solar system travels through the local interstellar cloud, a region of space where gas and dust densities are higher than average. This cloud compresses the heliosphere and allows more galactic cosmic rays to penetrate toward the inner planets. If we were to enter an even denser region, the added pressure could compress our protective bubble to the point where Earth experiences dangerous increases in radiation levels. Think of the heliosphere like an umbrella protecting us from a cosmic rainstorm of deadly particles. Sometimes the wind blows harder, and our umbrella gets turned inside out, letting more rain through. Other times, the storm intensifies, and even a perfect umbrella can't keep us completely dry. Our spacecraft, at the heliosphere's edge, serve as weather stations reporting on conditions in this cosmic storm. The long-term measurements from Voyager and New Horizons provide crucial data for understanding how the heliosphere's protective capacity changes over time. These changes affect everything from satellite operations to climate patterns to the long-term habitability of Earth. Increased cosmic ray exposure can damage the ozone layer, alter cloud formation, and potentially trigger ice ages or warming periods. The heliosphere also affects the entire solar system's ability to capture comets and asteroids from interstellar space. A strong protective bubble deflects most incoming objects, while a weaker heliosphere allows more interstellar visitors to penetrate our cosmic neighborhood. These visitors could bring new materials or potentially dangerous impacts to planets within our system. Understanding the heliosphere's dynamics becomes increasingly important as we develop technologies for interplanetary travel and consider establishing permanent settlements beyond Earth. Future human explorers will need detailed knowledge of radiation environments throughout our solar system and how they change over time. But maintaining contact with our distant scouts as they monitor these cosmic boundaries requires communication technology that operates at the very limits of what physics allows. Every day, radio signals carrying humanity's most distant conversations travel for over 22 hours across the void between stars, maintaining our fragile connection to spacecraft that have become the loneliest objects humans have ever built. The signals from Voyager 1, now over 14 billion miles away, arrive at Earth's radio telescopes as whispers, barely distinguishable from cosmic background noise. The spacecraft's radio transmitter produces only 23 watts of power, less than a typical light bulb. That feeble signal must cross distances so vast that light itself takes nearly a full day to make the journey. By the time Voyager's radio waves reach Earth, they have spread across such enormous distances that the total power collected by our largest antennas equals about 1/1,000,000th of the energy required to light a birthday candle. These signals are so weak that they would be completely overwhelmed by a cell phone transmitting from the same distance. Yet NASA's Deep Space Network can still decode the spacecraft's messages with remarkable clarity. The Deep Space Network consists of 3 massive antenna complexes strategically positioned around Earth, in California, Spain, and Australia. As our planet rotates, at least one of these facilities maintains contact with our interstellar explorers at all times. Each antenna dish spans 230 feet across, large enough to hold a football field, and can detect radio signals weaker than the energy released by a snowflake hitting the ground. Think of deep space communication, like trying to hear someone whisper from across a continent while standing next to a construction site. The desired signal is incredibly faint, while competing noise sources from Earth's atmosphere, electronic equipment, and cosmic radio sources threaten to drown out the message entirely. Success requires exquisite engineering and mathematical techniques that push the limits of information theory. The spacecraft use error correction codes that allow ground controllers to reconstruct complete messages, even when up to half the transmitted data gets lost or corrupted during the interstellar journey. These codes work by adding redundant information to each message, creating mathematical relationships that reveal which parts were damaged and how to fix them. But the greatest challenge isn't technical. It's simply the growing delay between sending commands and receiving responses. Instructions transmitted to New Horizons today won't arrive until tomorrow, and the spacecraft's acknowledgement won't return to Earth until the day after that. This communication delay will continue growing as our explorers venture deeper into interstellar space, eventually making real-time conversations impossible. Communicating across such distances also requires precise knowledge of each spacecraft's position and velocity. Radio waves travel in perfectly straight lines, so the antennas must point to exactly where each probe will be when the signals arrive, not where it appears to be when they're transmitted. Even tiny errors in position can cause complete communication failures across interstellar distances. The radio signals themselves carry more than just scientific data. They represent humanity's most distant conversations, our ongoing dialogue with machines that have traveled farther than any previous human creation. Each transmission maintains our connection to these lonely explorers as they venture into territory that no life from Earth has ever experienced. As the spacecraft age and their power systems gradually decay, maintaining these conversations becomes increasingly difficult. Engineers continuously modify communication protocols to extract maximum information from weakening signals, sometimes taking hours to transmit data that once flowed in minutes. The day will eventually come when these signals fade into silence, as the spacecraft's nuclear power sources finally decay beyond the ability to operate their radio transmitters. But even after communication ends, the nuclear systems that enable these conversations will continue to deteriorate in the cold emptiness of interstellar space. Deep in the heart of each interstellar spacecraft, radioactive plutonium slowly transforms into other elements, generating the heat that powers humanity's most distant outposts, while simultaneously counting down to their inevitable silence. The radioisotope, Thermoelectric generators, RTGs, aboard our interstellar explorers contain no moving parts, no fuel tanks, and no solar panels that could fail or be damaged during decades of travel. Instead, they rely on the steady decay of plutonium-238 atoms, which naturally convert into uranium over periods measured in human generations. Each radioactive decay releases a tiny burst of heat, and billions of these microscopic furnaces together generate enough energy to keep the spacecraft alive. When Voyager 1 launched in 1977, its nuclear power system produced about 470 watts, enough to power a small microwave oven. Today, nearly 5 decades later, that power output has declined to roughly 250 watts. As the plutonium fuel steadily transforms into non-radioactive elements, the spacecraft loses about 4 watts of power every year, a gradual dimming that cannot be stopped or reversed. Think of these power systems like cosmic candles burning in the interstellar dark. They were lit with enough fuel to burn brightly for decades, but the flame grows dimmer with each passing year until it eventually flickers out entirely. Unlike candles, however, the nuclear decay process is perfectly predictable. Scientists can calculate exactly when each spacecraft will fall silent. The gradual power loss forces mission controllers to make increasingly difficult decisions about which instruments to keep operating. Each scientific sensor, computer system, and radio transmitter requires a certain minimum power level to function properly. As available power decreases, engineers must shut down less critical systems to keep the most important instruments running as long as possible. New Horizons faces similar power constraints, but started its journey with more efficient systems and newer technology. Its RTG produced about 200 watts at launch and currently provides roughly 190 watts, enough to operate the spacecraft's essential systems until the late 2030s or early 2040s. The nuclear decay process also affects the spacecraft in subtler ways. As plutonium atoms transform into lighter elements, the total mass of the fuel decreases slightly, creating tiny changes in the spacecraft's center of mass. These shifts are so small, they require incredibly precise measurements to detect, but they can affect the probe's orientation and trajectory over decades of flight. The heat generated by radioactive decay also creates thermal stresses as different parts of the spacecraft expand and contract at different rates. Materials that seemed perfectly stable during ground testing gradually develop microscopic cracks and fatigue failures after decades of thermal cycling in the harsh environment of space. Even more challenging, the nuclear fuel gradually becomes contaminated with the products of radioactive decay. These new elements have different thermal properties than pure plutonium, slowly changing how efficiently the thermoelectric generators convert heat into electricity. The power systems become less efficient over time, even as the total heat output decreases. Engineers designed the power systems with enough margin to operate far longer than the original mission requirements. But they always knew this day would come. The nuclear fuel provides a finite energy budget that determines each spacecraft's maximum possible lifetime. No amount of clever engineering can extend their lives beyond what the laws of physics allow. When the power finally drops below critical levels, the spacecraft will shut down their transmitters and fall silent forever. But they will continue coasting through interstellar space for millions of years, carrying with them the messages and artifacts that represent humanity's first gifts to the cosmic community. These messages, designed to survive long after the spacecraft themselves have gone dark, may represent humanity's most lasting legacy to the galaxy. Attached to Voyager 1 and Voyager 2, two golden records contain the most sophisticated star maps humans have ever created. Cosmic GPS coordinates that will remain accurate for millions of years after human civilization has been forgotten. The Voyager golden records represent humanity's upgrade from the simple pioneer plaques, containing not just pictures and symbols, but actual sounds and music from Earth. Each 12-inch gold-plated copper disc holds 90 minutes of audio, including spoken greetings in 55 languages, natural sounds like thunder and bird songs, and musical selections ranging from Bach to Chuck Berry to traditional folk songs from around the world. But the record's most ingenious feature is its cover design, which functions as a cosmic Rosetta Stone that any scientifically advanced civilization could decipher. The cover includes a pulsar map, even more sophisticated than the one on the Pioneer plaques, a star chart that shows Earth's location relative to 14 pulsars scattered across our region of the galaxy. Pulsars are among the most precise timekeepers in the universe. These rapidly spinning neutron stars emit radio beams that sweep across space like lighthouse beams, creating perfectly regular pulses that can be detected from thousands of light years away. Each pulsar has its own unique pulse rate, and these rates slow down at predictable intervals as the neutron stars gradually lose rotational energy. Think of the pulsar map like a cosmic timestamp and address combined into one. The pulse rates shown on the record indicate exactly when the spacecraft were launched, while the pulsar positions reveal Earth's location in three-dimensional space. Any alien civilization that discovers these records millions of years in the future could use the pulsar data to determine both where the spacecraft came from and when they were sent. The map uses binary notation to represent each pulsar's pulse period and distance from Earth. Binary mathematics should be universal to any technological civilization. It's the simplest possible number system and forms the foundation for digital logic. The designers assumed that aliens capable of interstellar travel would necessarily understand binary arithmetic and be able to decode the numerical information. Even more remarkably, the pulsar map will remain accurate for millions of years, while the spacecraft will travel thousands of light years from Earth during that time. The pulsars themselves will continue broadcasting their regular signals with only minor changes in pulse rate. Future alien archaeologists could use the degraded pulse rates to determine exactly when the records were created, even if they're discovered in the distant future when pulsars have slowed down considerably. The records also include diagrams showing how to construct a record player capable of playing the audio content. These instructions use the same universal scientific constants, like the hydrogen atom's properties, that were used on the Pioneer plaques. The diagrams show the correct playback speed, stylus placement, and scanning direction needed to convert the recorded information back into sound. Creating these interstellar messages required solving unprecedented technical challenges. The golden records had to survive for millions of years in the harsh environment of interstellar space, resist corrosion from cosmic rays and interstellar dust, and remain readable by hypothetical aliens with completely unknown sensory capabilities and technological approaches. The audio content was selected by a committee led by Carl Sagan, who wanted to create a representative sample of human culture and natural sounds from Earth. The final selection includes everything from a crying baby to Beethoven's Fifth Symphony to traditional music from Peru, demonstrating the diversity of human expression and the natural world that produced us. Perhaps most importantly, the golden records represent humanity's first serious attempt to communicate across the vast gulfs of space and time that separate intelligent civilizations. They acknowledge that our species might be extinct long before these messages are found, making them both time capsules and tombstones, permanent monuments to a curious species that reached toward the stars. But these golden ambassadors are just 4 members of a much larger fleet racing toward different corners of infinity, each carrying humanity's hopes into the unknown. Across the cosmic dark, 5 human-made objects follow divergent paths that will carry them to different regions of the galaxy, spreading humanity's presence across a volume of space larger than entire stellar empires. Pioneer 10 leads our interstellar fleet toward the constellation Taurus, racing toward a rendezvous with the red giant star Aldebaran in roughly 2 million years. By that time, the spacecraft will have traveled 68 light-years from home, farther than most of the stars visible in Earth's night sky. If Aldebaran had no motion of its own, Pioneer 10 would pass within about 1.1 light-years of the star, close enough for any alien civilization there to detect the probe's passage. Pioneer 11 follows a different trajectory toward the constellation Aquila, heading for a much closer encounter with a nearby star. In about 4 million years, the spacecraft will pass within just 0.4 light-years of a small red dwarf star called Gliese 745. This will be the closest approach to another star of any human-made object for millions of years, potentially bringing Pioneer 11 within range of any planets orbiting that distant sun. Voyager 1, humanity's most distant ambassador, races toward the constellation Ophiuchus at 38,000 miles per hour. In approximately 40,000 years, it will pass within about 1.5 light-years of a star called Gliese 445 in the constellation Camelopardalis. While this sounds like a close encounter, it's actually about 60,000 times farther than Earth orbits our Sun, close only by interstellar standards. Voyager 2 follows its unique southern trajectory toward a different region of space entirely. In about 40,000 years, it will approach within 1.5 light-years of the star Ross 248 in the constellation Andromeda. The 2 Voyagers will thus become humanity's first emissaries to completely different stellar neighborhoods, doubling our chances of making contact with alien civilizations. New Horizons, the youngest member of our interstellar fleet, currently heads toward the constellation Sagittarius, but will require hundreds of thousands of years to reach the distances already achieved by the Voyager probes. Its trajectory will eventually carry it into the dense star fields near the center of our galaxy, where the chances of encounter with other stellar objects our high systems are much higher than in our current sparse stellar neighborhood. Think of these 5 spacecraft as humanity's first attempt at galactic colonization. They are not carrying people or even life, but spreading our ideas, music, and scientific knowledge across distances that will never be crossed by human travelers. They represent seeds of human consciousness scattered into the cosmic wind, hoping to take root in alien minds millions of years in the future. The scale of their divergent journeys defies human comprehension. By the time any of these spacecraft approaches another star, our Sun will have completed multiple orbits around the galaxy's center. Entire stellar populations will have been born, lived, and died. Ice ages will have come and gone on Earth. Human civilization, if it survives, will be as different from today's humanity as we are from the first bacteria that crawled from primordial seas. Yet, these 5 tiny ambassadors will continue their patient journeys, carrying with them the hopes and dreams of a species that dared to reach beyond its planetary cradle. They bear messages designed to outlast the civilizations that created them, golden records and plaques that will remain readable long after the last human has been forgotten. In the unimaginable future, when our Sun has exhausted its nuclear fuel and Earth has become a frozen wasteland, these spacecraft will still be racing through the galaxy. They will serve as monuments to human curiosity and creativity, proof that intelligence once arose on a small blue planet orbiting an ordinary star in the outer reaches of a typical spiral galaxy. The discoveries made by our furthest satellites have transformed our understanding of the cosmos and our place within it. They revealed that space is not empty, but filled with wonders, that planetary systems are more complex than anyone imagined, and that the journey between stars holds mysteries we are only beginning to comprehend as they continue their eternal voyages into infinity. These brave explorers carry the essence of humanity itself, our insatiable desire to explore, to question, and to reach toward the unknown. For more journeys to the edge of everything we know, make sure you subscribe to Stellify Science.